Hey guys, I'm making this video in response to a student request, which reminds me that if you ever have something you want some more info on, if I deem it worthy or definitely a good question, I'll make a video. Lewis acids and bases, what the heck are they? Another name for Lewis acid is an electrophile, something that likes electrons or is seeking electrons. It could be positive, it could be neutral, sometimes it could even be negative, but there's got to be some other negative overall, but there must be some site somewhere that's attracted to more electrons or a site of higher electronegativity. Conversely, the opposite would be, what's a Lewis base? We also call it a nucleophile. If this Lewis acid is an electrophile, what's the opposite of an electron? Is a proton or a nucleus. So I say, what's a Lewis base? Any species, usually negative or neutral. If it is neutral, it must have some sites where the lone pairs attract the positivity of a nucleus, or a region of lesser electron density called electropositivity. Sounds like I just made that word up, doesn't it? But this means nothing without a whole bunch of practice. So let's just scroll through some pictures. Here's a classic Lewis acid-base reaction. This is a region of extra lone pair, high electron density. There's no charge here overall, nor here. But if this boron being electron deficient would not mind gathering up another another electron pair, so as to form an extra bond, because it only has 2, 4, 6 right now. The octet is 8. So in that reaction, the electrophile attracts the nucleophile. Or I could say this is attracted to the nucleus of the boron. This is attracted to the electrons of the lone pair on the nitrogen. Forms a new bond. That's a classic, super classic example. You'll see that in every textbook you ever look at. Lewis acids and bases. Other examples, positive metal ions in the water. Lewis acids. Anything negative or negativity to it. This could bond on through the nitrogen, or it could bond through the carbon. This could even turn sideways. This cyano group, cyanide ion, can turn sideways, and that pi bonding right there can also bond to the silver or be attracted to the positivity of the silver. So this is not an uncommon complexed ion. Here's another one. OH minus can serve as a ligand because it's attracted to the lead 2 plus. Lewis acid, Lewis base, negativity, complex ion. Here's another one. Nickel. Nickel ion in the water. This is an NO2, a nitrite ion. That's got all kinds of negativity to it. It could be attracted to the nickel, the Lewis bases, through the oxygen or through the nitrogen. So that lone pair could be attracted to the nickel, or all these lone pairs on this oxygen could be attracted to that nickel. Makes a cool octahedral complex. Lewis acid, Lewis base. My final inorganic example. Here's ethylene diamine tetraacetic acid. These H's float away under basic conditions and leave this big molecule that has 1, 2, 3, 4, 5, 6 Lewis base sites that are then attracted to and totally surround many metal ions. Here's a metal ion, and here's the ethylene diamine tetraacetic acid, and that binds really strongly to that metal. Let's go to organic chemistry for a while. Look at some examples. Organic chemistry. Let's see, organic chemistry. I took this honestly from an organic chemistry textbook. Bronsted-Lowry acids or Lewis acids. Well, Bronsted-Lowry say contain a proton. I like the Lewis definition more. Why am I going with this? Anyways, check these out. Negativity, 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 negativity. Acid, positivity. Giving up the proton, giving up the proton, giving up the proton, giving up the proton. One thing organic chemists are known for doing is looking for locations where I could donate a hydrogen ion, or lone pairs could take on a hydrogen ion. Sometimes we say that since this weak acid HA is not exactly uniform, the A is the slightly negative, the H is the slightly positive, that this base, having a lone pair, could be weakly attracted to that H, and indeed creating a conjugate acid, leaving behind, this is the conjugate acid of this base, but this is the conjugate base of this acid. I think we've seen that before in lecture, but like I said, more examples never hurts. Water can also function as an acid. This negativity here attracts that hydrogen. They'll often draw arrows in the direction the electrons are traveling. Here the electron is pushed sort of over onto the oxygen, or the oxygen is electronegative enough to suck off the electron off of the hydrogen. And that's is assisted by the fact that this lone pair is attracted to that hydrogen. And you see the transfer. Negativity, positivity. Yeah. Nothing else to add there. Same story here. This negativity is drawn inward in a sense sometimes, but also that triple bond can, well, I won't say that right this minute. I'll just say interesting how that can work like that. This would be a super strong base right here, because it looks like this ending terminal carbon has lost one of its hydrogens. The H plus is left, leaving behind a very strong base, because that would have been a very weak acid. Let's see. Oh yeah, negativity. It doesn't seem like there's any negativity there, but when you think about the structure of what that pi bonding and what's happening there, some extra electrons looking for some trouble to get into or something to do. And same story here. Triple bond, double bond can often function as a Lewis base. Lewis acids can give up a hydrogen, can't give up a hydrogen, so it's not a Bronsted-Lowry acid, but it certainly can look for regions of negativity. So it's an electron pair acceptor. Aluminum and boron do the same thing. Oxygen bases with plenty of lone pairs, nitrogen bases with lone pairs on the nitrogen. Say no more. This is another famous example. Lone pairs, Lewis base, Lewis acid attracted. This is seeking that electrophile. This is a nucleophile. Let's see, if this is a bromide ion, lots of extra negativity to donate to that, Lewis acid. Same story here, lots of electronegativity to donate to that, forming a bond of some kind, right? But how common is that? Not very common. You can do it though. All right, also double bonds. Like I said, this double bond here, resulting from the sideways overlap of unused p orbitals and electron looking for something to do, that pi bond can serve as a Lewis base. Let's say this thing was in the vicinity. Well, this positivity is attracted to that negativity. Lewis acid, Lewis base, and we see the electrons are left with the chloride, and that hydrogen is kind of snuck over onto one of those carbons there. Again, double bond, or triple bond can function as a bit of a Lewis base, often looking for some regions of positivity, or let's see, double bond, Lewis base. This XY could be something that's electronegative. Could have some negativity to it, but in essence it's searching for extra electronegativity, and that could search for this. Here's a summary of some of the things that can happen with that double bond. And boy, if I had extra time, I'd make a little addition to this. But because if you take something like bromine or chlorine, very reactive, and add them to this double bond, it breaks that bond and adds the bromine or chlorine right across there. Sulfuric acid, a halogen, HX, HCl, HBr, HI, add across a double bond as well. In a sense, this functions as a Lewis base again, and since this functions as a Lewis acid. And The HBr can add to that double bond. The HCl can add to that double bond. Lewis base, Lewis base, Lewis acid, Lewis acid. And I think I'm going to skip those mechanisms. You can look at them if you get time. I'll put it on the PDF. Oops. Sorry about that. And how many examples can we give? We can give lots of examples. Lewis base, Lewis acid, chlorine or bromine, chlorination, bromination, halogenation of a double bond. It can happen with a triple bond as well. Again, I think I'll skip that mechanism. It's interesting how it works like this, but the bottom line is the reactive chlorine or bromine or halogen functions as a bit of a Lewis acid. Chlorine, bromine, iodine, adding to that double bond. Yeah. Again, I'm scrolling past those mechanisms because don't think it's terribly necessary to think about it, but good to think about where the electrons are being attracted. Lewis base, electron pairs attracted to that deficient boron. That's very common. We've seen many examples of that already. Hydroboration, boron, that's looking for some negativity. Why doesn't it attract to that? Indeed, it does. So this Lewis base, Lewis acid, let me end with some pictures. If I don't have sufficient hydrogens on these carbons to allow the covalent bonding, the sigma bonding, then this unused p orbital, this unused p orbital will sideways overlap with this unused p orbital, and this unused p orbital will overlap with this unused p orbital in a way very similar to this, or maybe you can imagine 3 dimensions like this. So the pink unused p orbitals are overlapping, and the blue unused p orbitals are overlapping. And oh shoot, hang on just a second. Let me pause. All right, am I there yet? No, I'm not there yet. I apologize. All right, we're there. And as I was going to say, finally, let's look at this one. Here's my 3-dimensional. The purple is 1 pi bond, the blue is another pi bond, the gold is the sigma bond, and we're saying that that has a high region of extra electron density, and even though it seems like these have enough electrons already, they would really rather become chloride ions in a sense, or share some extra else with someone other than themselves. And in a way, if you look back up here, Lewis acid, Lewis base, we see how that can possibly happen with all these mechanism examples, etc., etc. So, all right, guys, thanks for watching. Seriously, thanks for watching.